Now that we've covered syslog and logrotate, and of course we'll revert to both as well as other things throughout our studies as time progresses and more data are collected, let's spend some time covering common networking utilities. Now we know that Linux is all about networking, and that means it includes tens if not hundreds of networking utilities. Utilities that allow you to access the wealth of protocols that are freely available. But of course, the primary emphasis is placed on TCP/IP, including IP version 4 as well as IPv6. So prior to getting into the differences between v4 and v6 and how they're implemented on Red Hat Enterprise Linux, let's warm you up to some utilities that are very helpful. So we'll label this section Common Network Utilities. And these are very common utilities, and again, there are tens if not hundreds of utilities. So by no means are we attempting to cover them all, but just some key tools that can help you to troubleshoot and diagnose network connectivity issues in your environment. So features includes useful for basic troubleshooting. So with that said, let's begin with an age-old utility, ping. Ping is really an acronym, although it's often referred to in the lowercase for Packet Internet Groper. So it gropes the target hosts by sending ICMP echo requests and expecting ICMP echo replies. So, features ability to communicate with hosts using ICMP. A, ping sends ICMP echo requests, and B, ping expects to receive ICMP echo replies. So for each echo request singular sent to a target, ICMP echo reply singular is expected. But a series of ICMP echo requests are usually sent, such as 3, 4, or in the default configuration, an indefinite number of ICMP echo requests are sent to the target, and an indefinite number of replies are expected. At the end of it all, when you break the process, or after having specified a certain number of ICMP packets to send and receive, ping will produce a report which includes information related to the response received from the target. So we know what our network layout looks like. It includes a default gateway as well as other hosts on the network. And with that said, we can attempt to communicate with them. But just in case you've forgotten, let's just navigate to our document and bring it up on the screen as a talking point. So here's the classroom topology. This is the topology that we use for most of our classroom environments. And again, we're currently logged on to Linux CBT Serve 1, the Red Hat Enterprise box located at .1. And from that box, we can communicate with a multitude of boxes throughout our environment. So for example, we can ping the default gateway, which is always a test to see whether or not you have connectivity outside of your network. We can ping our local instance, our local system. We're currently logged on to this box here. So let's just zoom in a little bit, and again, we're on this box. We can ping ourselves, our neighbors, including the default gateway, including hosts in the DMZ, and possibly hosts on the internet if the firewall doesn't prevent us from doing so. So let's set up some basic tests. Ping some hosts and evaluate the output. So 1, we'll ping localhost and see how that behaves. Localhost translates to the loopback adapter's address, which is 127.0.0.1. In fact, the entire 127 subnet is reserved for the loopback adapter. So you can ping any IP address on this 127 network, and your local loopback adapter will return. So with that said, let's navigate to our shell and proceed to generating some ICMP echo requests. We'll just find this in the background here, and we'll find a window on our local system, not the remote system, and clear screen, reset the buffer. So by default, when we ping localhost, for example, it sends an indefinite number of 64-byte ICMP packets, and it expects an indefinite number of ICMP echo replies. Here we see the sequences, and they are listed in sequential order, with time to lives associated, or time to live values associated with each ICMP echo request, and the total amount of time the round trip packet took. You break this process by executing Control+C. At the end of it all, a total number of transmitted packets as well as received packets are returned. In addition, the percentage of the packet loss, which in this case is excellent 0%, is returned. The total amount of time it took to send the 32 packets is just actually under 32 seconds that is, just under 31 seconds. It took 30,992 milliseconds, which is equivalent to just under 31 seconds to send 32 packets. Generally, ping sends packets in 1 second intervals. So when we run that again, you can count it. It's pretty much a second between each, and between each round trip. So when it gets a reply, that's roughly a full second. This may not always be the case when pinging hosts across your intranet or across the internet, but generally speaking, you can expect to receive a full response in under a second. Again, the full time is returned per interval. In this case, 22 packets were transmitted and received in under 21 seconds. More statistical information is provided at the end. The round trip time, the minimum, average, maximum, the maximum deviation. So the minimum out of this entire block of pings was, as you can see, 60/100ths of a second, or 0.061 of a second. The average was 68/100ths of a second, and that's the minimum round trip. The max was 74/100ths of a second, and the maximum deviation was, as you can see, 0.009, tenths, hundredths, thousandths, 9,000ths of a second. Now you may alter ping to send a specific number of ICMP requests. Let's scroll down. Again, this is a very simple tool, but it's a very important tool. By using the C option, lowercase, and n number of packets, such as 3, followed by the target, will send 3 ICMP echo requests. So sends 3 ICMP echo requests, which means it expects 3 ICMP echo replies. So there we see the second and now the third, and we can take a look at the values. The minimum is indeed 65/100ths of a second, 0.065. The average, 0.67, that's the difference between the 3, or the average between the 3. The maximum is 0.069. So the values indeed make sense, and they correlate to the actual packet sent. Now when you ping localhost, the keyword localhost, name resolution takes place. We should just note that. Although it's slightly deviating, note ping localhost performs name resolution using etc hosts. etc hosts stores static name to IP mappings. It is like having your local or your own DNS server for your own needs or for exclusive usage. A cat of etc hosts reveals a set number of hosts, including localhosts. Localhost is always included in the hosts file by default, by virtue of installing the operating system, so that when you reference localhost using tools like ping or any other tool, SSH, LFTP, you name it, it really translates to the IP address 127.0.0.1 with the help of the etc hosts file. Now, we also mentioned earlier that if you were to ping any other 127 address, the system would respond. Your local system, your local IP stack would respond. Let's try that out. We'll send 3 packets to 127.0.0.2. And again, it responds, which proves that the entire 127 subnet is bound to the local loopback interface. You can pick any address that you'd like on the 127 network, and your local IP stack will respond accordingly. Here's a random pick of .25, and our local stack has again responded. So 127 is a local network. Note 127.0.0.1 and the full subnet, the full /8, so 127.0.0.1 or 0.0.0/8 is fully reserved to the loopback adapter of all IPv4 hosts, regardless of operating system, whether Windows, Linux, FreeBSD, Solaris, you name it. So long as it conforms to IP version 4 specifications, you'll be able to communicate with any 127 network, and you're really communicating with the local network card. So what does that mean with respect to this graphic? Well, we're currently connected to this Red Hat Enterprise 5 box. This is where we're doing most of our work. And from here, we connect to other systems, such as the VMware instance running on our other server, this SUSE Enterprise 10 box, which has a Red Hat instance. When you ping your loopback adapter using 127.0.0.1, you're really pinging internally to this box. You're not generating traffic out onto the network, to the first switch, up through the GBIC, to the second switch. None of that takes place. You're in fact pinging the local system's loopback adapter, and it's kept local, and it's designed to be kept local. So how about pinging remote systems? Well, that's quite easy. We'll ping sending 3 packets to a remote system's IP address, 192.168.75.199, which is the Linux CBT Serve 4 box, which happens to be a VMware instance of Red Hat Enterprise 5. Let's give this a try. We'll clear screen. By the way, you don't need to be root to run ping. You can do so easily as a non-privileged user. And again, we see traffic information. However, the traffic information should be lengthier, longer, taking more time, as now the traffic has indeed traversed the networking topology. In this case, we pinged from our local system up through the 100 megabit link to the switch, up through the GBIC to the other switch, over to the SUSE Enterprise 10 box's VMware instance. That's this SUSE Enterprise 10 box's VMware instance. So there's a little bit of traveling, which explains the differences we see in time. Notice that in the case of the first ICMP echo request and reply, we see the time as 3.68 milliseconds, as instead of fractions of a millisecond. We see that for the second ping, it was a fraction of a millisecond, because usually after you've communicated or set up communications with a host using ICMP, TCP, UDP, any protocol, subsequent communication streams tend to be quicker. The setup stream, the first packet, tends to take a longer time, but once the host is up and running and responding, communications speed up. The third, although faster than the first, was slower than the second, but still fast in the overall scheme of things. And then we get the fact that we lost no information, and it took just under 2 seconds to send 3 packets. Here's the round trip timing for the minimum, the average, as well as the maximum and deviation. So we have a deviation of just over 1 full second. Makes perfect sense. It took us 3.68 milliseconds, and a fraction of a millisecond, then 1.74, and when calculated, it's roughly a 1.284 millisecond differential, not second differential, millisecond. So it was a deviation of 1.284 milliseconds as opposed to 1,000, meaning 1 full second. as 1,000 milliseconds is equal to 1 second. All 3 packets did indeed take 1,998 milliseconds, or just under 2 seconds. So again, we use ping for the purpose of communicating with remote systems. Ping supports many options, not just a packet count as we've shown you, or the ability to send 3 packets. But you could, for example, set the interval. Let's say you wanted to run a process which checks up on a host on an interval that's wider than a second, as is the default for ping. Well, using the interval option, we can change that to make it longer, for example. Let's go ahead and give that a try. And we see the I option here. We're going to set that as our next task. So ping, and let's suppose we want to send 3 packets. With the I option, let's say instead of every 1 second, every 3 seconds, the same host. This will stall or delay the pings, or spread them apart by 3 seconds as opposed to 1 second, which again is the default. Let's clear screen. And now the timing in between the first and second is 3 seconds, the second and third is 3 seconds. But the timing doesn't impact the round-trip minimum average and maximum deviation. The time that it takes to send 1 ICMP echo request and receive 1 ICMP echo reply is solely based on the network connectivity between the 2 hosts, not the interval that we've specified. So it still takes us a very short amount of time, generally under a full millisecond, to communicate, even if we spread out the ICMP requests. So that way we can again spread out our pings. Let's set it to 5 seconds. The first will go immediately, then 5 seconds later the second, and then 5 seconds later the third. But again, it doesn't impact the round-trip timing. The round-trip timing is a function of the network connectivity between the 2. So delays pings to 3 seconds apart, which can be useful if you are monitoring a remote system and elect not to send packets using the standard 1 second interval. So let's just note ping defaults to a standard 1 second interval. You may want to alter it. Now there are other things you can do obviously with ping, especially with Linux. For example, you can influence the byte size that you send, the packet size. The default packet size, as you saw before, is 64 bytes, but not all hosts support 64 bytes. You may need to reduce the size to, let's say, 32 bytes, and there is some overhead, an 8-byte overhead, making it 40 bytes. So if you need exactly 32 bytes, drop it by 8 to 24 with its overhead of 8 bytes will then yield 32-byte packets. So with Linux ping, you can, or any Unix ping, you can influence the size of the packets using the S option. So again, ping is a useful diagnostic utility, but you can't always rely upon it, because for example, we're on this system on one subnet, and if we attempted to, let's say, hit a host on the internet using ping, and the router disables ping, then ping will never get the ICMP echo reply. So you can't always rely upon it because firewalls may block it, which is why there are other protocols. For example, in addition to ping, we've got Telnet. Now we don't advocate that you use Telnet for taking control of a remote system because it's a clear text, unsafe protocol. However, for diagnostic purposes, Telnet is an excellent tool, and it's great for basic TCP port diagnosis. It's an excellent tool for this because if you have connectivity problems to, let's say, a TCP port that you know should be accessible, rather than using the client application that connects to the port, you can use Telnet to try to connect to the port. So, connect to ports on various hosts. By connecting to those ports, you'll be able to determine whether or not the port is listening. It's equivalent to a TCP connect performed by tools such as Nmap. when logged in non-privileged mode or in privileged mode, and you elect to by indicating the appropriate option to Nmap. Now let's try a simple test. We've got multiple systems on the wire, listening to protocols such as 22 for SSH, 80 for web, and others. So from our system, let's test the ability to communicate with, let's say, one of the SUSE boxes on port 22 without using the SSH client. This is where Telnet helps us out. Telnet, let's say 192.168.75.100 followed by the TCP port. Instead of port 23 for Telnet, we'll indicate 22 for SSH. And what this will do is connect us to the port. And we will usually see a banner for the service behind the port. Let's try this. In fact, we'll try it in a new window as the non-privileged user, Linux CBT. So let's Telnet, and there you see the banner, the SSH banner of the remote system. This tells us positively that the remote system is listening to SSH and will accept connection. So if someone argues or complains or makes note that they're unable to connect to a port on one of your systems, you should be able to easily tell that to that system to see whether or not it's indeed listening. And this also applies to internet-based hosts. So for example, let's use one of our public web servers. We'll telnet to www.linuxcbt.com on port 80, which is a web port, which should be listening so long as the website's up and running. Using the same shell, we'll paste the command, and there we see the remote system has picked up the phone, and if we echo the escape sequence, the default page will be dumped for the index.php page. So with that said, you can use Telnet to connect to TCP ports. Connect to, and we should indicate, TCP ports on various hosts. It doesn't work with UDP, as UDP is connectionless. It doesn't support connection statuses. So you can connect to TCP ports, whatever you'd like, even SSL ports, to see if it picks up. For example, a Telnet to www.linuxcbt.com on 443 will pick up the phone, as it indeed returns for SSL. That doesn't return anything to our screen because it's all encrypted, it's garbled, but nonetheless tells us that the port picks up. Now, how about connecting to a port that is not in use or is not active on one of our internal hosts, such as 2222? Telnet returns a connection refuse, and this is where you see its value as a diagnostic tool. Because if a port is listening, you should not receive connection refuse. But if it's not listening or not available for one reason or another, then you'll get connection refuse. And by one reason or another, we mean, well, you need to keep into consideration or take into consideration that there could be intermediary firewalls preventing you from connecting to the service. There may even be a firewall at the host denying access. But as a general test, you can use Telnet to communicate with the port to see if it is indeed available. There's still yet many other tools. Let's move on to Netstat. Netstat returns network statistics. It provides network connection information, and it does so based on the values in PROCnet or /PROCnet. So it provides network connection information. And by network we mean all protocols supported, TCP, UDP, IPv4, IPv6, and so on. Even for Unix sockets and other protocols, but we generally use it for IP as Linux is synonymous with IP. So information from PROCnet star. That's where it gets its information from, and it presents it to us nicely in a nice, neat format. So task, return useful information for various protocols. So for example, Netstat, with nothing, with no options, will attempt to return connection information. Let's go to a shell. And you can run this tool also as a non-privileged user, but you get more information when you run it as a privileged user. When you run it in this form, it returns everything. Unix streams or Unix sockets, datagram connections for Unix, as well as TCP UDP. We often need to filter the information because it returns way too much information, and that's why we run its many other forms, such as netstat-a. Let's return to the shell. And if you pipe this output to less, then you get it one page full at a time. Netstat-a dumps all information, and it also resolves hosts and ports wherever possible, such as the Internet Printing Protocol, SMTP, and others. Here we see TCP connections returned first. We see the receive and send queues, the fact that the protocol is TCP, so it's sorted by TCP first, the local address, the foreign address, and the state of the port. The state of the connection in this case, which happens to reflect the state of the port. If you scroll through the list, following TCP is information for UDP, which has nothing in the state field because it's connectionless, doesn't support connection status information. However, there are services bound to UDP, such as syslog, DHCP, and others that are very important. After TCP and UDP, we then see Unix domain sockets for various programs like syslog, MySQL, various programs that make use of Unix domain sockets. So that's using netstat-a, that is, returns all protocols. But again, it's still not concise enough. It still doesn't return information in a nice, easy to manage, digestible format. Again, netstat-a returns all protocols / sockets. Now, if you want to zero in on specific protocols such as TCP, which is generally where we tend to use, or the protocol that we tend to zero in on with netstat, then use netstat with the NTL option. This will 1. Turn off name resolution, 2. Focus on TCP, and 3. List the various listeners. So this returns all listeners. The purpose of returning all listeners is to see what ports your system is listening to. This tells you for the TCP protocol that this local system is listening to the following ports: 2208, 5801, 5900, 5901, 111, 6001, so on and so forth. Each of these protocols, of course, have distinct purposes, but indeed, our system is listening to these ports. 22 we can confirm, that's used for SSH, and the triple or quadruple colons that we see here, the triple colons that is, represents IPv6 and IPv4 connectivity. 25 is for SMTP. If we turn on the P option to NTL, it attempts to return the program that has bound to the port. So let's reset the buffer and execute P, and then for each listener, notice that the state for all of these ports is listen, not established or some other intermediary state, but listen. We see that the different programs that are responsible for the port, such as 631 for CUPS, for printing, for the Internet Printing Protocol, are returned. Now, if you want to see name resolution, take off the N option. When you take off the N option, it attempts to return the names, such as TLP. This tells you the name of the host as well as the name of the protocol. We should also note that the names of the protocols come from ETC services. Let's just return to the shell. In ETC, there is a services file which translates various ports, TCP and UDP, to names, such as FTP data, FTP, SSH, Telnet, you name it. So we should just note that. Netstat uses ETC services to translate ports to names, and so do many other TCP/IP related programs. We disable name resolution by using the N option, so it returns all listeners without name resolution. If you want name resolution, drop the N option. Now, how about focusing in on, and this, we should just note that this focuses on TCP listeners. How about UDP listeners? Sometimes you want to know what UDP ports your system is bound to. netstat NULP returns all UDP listeners. Again, listeners are programs that our system is listening to, or ports that our system is listening to. In other words, ports that our system will service if we connect locally or from a remote system, versus sockets that are used for general communications, like established sockets. Let's examine the UDP listeners. Here are the UDP listeners, including syslog, which we know, port mapper, which serves for RPC services, a couple RPC listeners, CUPS, and others. So these are the UDP listeners. There is no state information because UDP is connectionless, meaning it doesn't maintain state information. TCP does. Whenever you see a listener on all zeros, it means any IP address defined on the system will accept traffic to that port. So for example, in the case of syslog, for each IP address defined on this system, syslog will accept traffic to any of those IP addresses or all of those IP addresses. So let's just note that. This means that syslog will accept traffic to any of the defined IP addresses / interfaces on the system. That's what the all zeros mean. There are ways to tweak, however, for security purposes, and we'll show you in the security section, services so that they don't bind themselves to all IP addresses. And this is possible with most, if not all, TCP/IP compliant operating systems. But just bear that in mind that if you are running syslog and you see all zeros, or any service for that matter, such as CUPS, for any IP address defined, which you can tell using ifconfig, and in this case it's 192.168.75.10 as well as 127.0.0.1, as well as the IPv6 addresses. So for any of these IP addresses, local IPv6 or IPv4, syslog, CUPS, and other programs that are bound to all zeros, whether TCP or UDP, will accept traffic on those IP addresses. Keep that in mind from a security perspective. Now, if you want to see sockets that are in place, execute netstat. Instead of with the NTLP, for example, drop the L option. Let's give this a try from the shell. This will also return the programs responsible for those sockets. Here are actual connections, not just listeners, but connections between a given source and a given destination. For example, this shows us that from our local system, 192.168.75.10, on a high port of 56,406, we have an outbound established SSH socket to Linux CBT Media 1 or 192.168.75.100 on its SSH port, and the session is established. We also have an SSH session, in fact, 2 SSH sessions established on the other Red Hat Enterprise system. We also have, as you can see below, an IPv6 session established for SSH back on our local system. So from the remote system, there's an SSH session back to our local system using IPv6. So executing netstat with the NT option or NTP option returns established connections or sockets. This tells you what's currently connected on your host. That's very important, as you can tell who's connected. Let's say you need to administer the system and you need to take a service down like SSH. You'd use netstat NTP to determine if there are any SSH sessions. Now, no need to look at all of this output, just grep 22. And you'll see only instances of 22, so this tells you what's going on in the world of SSH on the box. And then you'll need to make the determination as to whether or not the sessions are outbound or inbound. Whenever you see traffic terminating on your local 22, that means it's inbound. Whenever you see traffic terminating on a remote system's 22, in other words, an IP address for a system that doesn't belong to your system, then it means the session is outbound. and then you'll be able to make the determination as to whether or not you can take down your service. So that's why you use the netstack command. There's another useful command, the address resolution protocol command. This command resolves layer 2 of the OSI model, MAC addresses, to layer 3 of the OSI model, IP addresses. There are two different addresses in the OSI model. However, MAC addresses or layer 2 addresses are burned in or uniquely identified or associated with network interface cards or NICs. We can return this information using ifconfig. So task includes examine MAC addresses using ifconfig and ARP. Now, before we do so, let's just return to the graphic to explain what happens. When we decide from our Red Hat Enterprise 5 box, this system, Linux CBT Serve 1, to initiate a connection, let's say outbound to the Debian box or outbound to another Linux box, our system uses layer 3 of the OSI model, or an IP address, to communicate with that remote host. So in our SSH session out to, let's say, the SUSE Enterprise box with the 100 address, we've used 192.168.75.100 IP version 4 address to communicate. However, hosts really communicate at a lower level of the OSI model, layer 2. And each host has a unique layer 2 address. It's a 48-bit MAC address. Again, that address is uniquely identified or assigned to the network interface card or cards plugged into the box. So in fact, an IP version 4 address as well as an IP version 6 address is just an overlay or an abstraction or a topical or another way of referencing a system that's human readable or makes more sense or is more logical and allows for hierarchy. In other words, the distinction between an internal versus a DMZ versus an internet network. So indeed, our applications communicate initially using names then IP addresses, but all resolution comes down to the MAC address. And that's why it's important to know the MAC address or know how to get information about the MAC address of your local system and remote systems. But of course, all this information is taken care of for you and maintained for you using ARP. So when we make a request from our system to the SUSE Enterprise 10 box with the 100 address, an ARP request is made by the IP stack, which translates 192.168.75.100 to a distinct MAC address. Then communications proceed based on those MAC addresses. And ditto for connecting out to the DMZ or remote subnets like the internet. When we attempt to communicate, let's say, with a DMZ host, we attempt, or the IP stack translates the IP address to a MAC address. But if the IP address is on a remote subnet, then the MAC address of the network interface of the router that's connected to our subnet is stored in our ARP table. ARP takes care of this for us. It's a service provided by TCP/IP, but we should still know how to get access to that information. So first and foremost, let's examine our MAC address using ifconfig. This returns our local MAC addresses. We'll return to the shell and then execute ifconfig. Now for each network interface, ETH0 and loopback, you'll see different information. But the interface that actually communicates using MAC addresses out onto the network, whether on the local network or remote subnet, is one of your routable interfaces, such as ETH0, Ethernet 1, Ethernet 2, and so on. ETH is short for Ethernet. LO is short for loopback. So ignore the loopback interface. This interface is always used locally, and focus on your Ethernet or token ring or other types of interfaces like PPP, your routable interfaces. Notice that this Ethernet interface, ETH0, which is the lone routable Ethernet interface in this box, has a hardware address. This is also the MAC address. Has a hardware address of the following: In fact, let's just copy the entire line. And this MAC address represents the layer 2 address of the system. So we see the output, ifconfig returned, and it returned, again, the fact that the encapsulation is Ethernet for the interface, and it has a hardware address, which is the MAC address of the 48 bits that you see here. Each of these sections represents 8 bytes. Each half represents 4 bytes, or a nibble. So 4 bytes, and if we count the sections, there are 6 sections times 8 equals 48 bits. This MAC address, this full 48-bit representation, or 6 bytes, is unique to our network interface card. And when we communicate with our local system using its routable IP address, or Ethernet 0, or with a remote system using its Ethernet interface, there's a translation between IP addresses and MAC addresses, which is why we use the ARP command to reveal the values stored in that table. But it's maintained automatically for us, and very seldom will you need to actually hardwire entries. The ARP table is updated dynamically, so that means if you don't communicate with a host for a certain amount of time, then the entry will be removed until subsequent communications are attempted. Here we see an entry for 199. This is one of our SUSE box, well, one of our Linux boxes, a Red Hat Enterprise box, that is. Its MAC address is the following, and it's accessible via Ethernet 0. Here's another Linux box at 101. Or this, in fact, this is a Windows box at 101, which has a distinct MAC address. Here's the router's IP address, .1, and it also has a distinct MAC address. We see an incomplete entry for Linux CBT Deb2 because it's currently not turned on for an IP address of .175. And we see an entry for Linux CBT Media 1. Wherever possible, name resolution takes place. So here's the layer 4 information, Linux CBT Media 1 for its IP address, which translates to its MAC address. But no need to believe the MAC or the ARP table's entries. Connect to the host and examine for yourself. So for example, for this 199 host, which is a Red Hat Enterprise box, we should still have an SSH session open to it, and we do. That's here. Let's clear screen and execute ifconfig. Then we'll see that the MAC address terminates with 1692. Let's see if that's the case here. There it is, 1692. So our local system knows how to get to 192.168.75.199 using Ethernet 0 and the following MAC address, which terminates with 16:92. And we've confirmed using ifconfig on a remote system that indeed its MAC address ends with 1692 and its IP version 4 address is indeed 75.199. We may also confirm the MAC table, the ARP table on the remote system by executing ARP-A. It should include an entry for our host system, .10, with its MAC address, and it does. But no need to believe the ARP table. Return to the local system, execute ifconfig, and you'll see that indeed 4108 is the MAC address. So when two hosts communicate, they exchange MAC information. This returns MAC to IP mappings. So note, when two TCP/IP hosts communicate, ARP is performed to translate the IP address, and this may be v6 or v4, to a MAC address, which is layer 2. Also note, if one or more routers separate the communicating hosts, which means there's hierarchy or subnets involved, then the MAC address of the router's interface is stored by each client. And we should note the MAC address of the default routers or gateways interface is stored by each client. and then the router is responsible for translating subsequent lookups of IP addresses to MAC addresses for subsequent routers if necessary. So as the hops are translated, for example, if we communicate with an internet site from our internal box, we indeed find out the MAC address is the interface of the router because the IP address is on a remote subnet. So we store that MAC address of the interface of the router. Then the router goes ahead and looks up on the internet its next hop and stores the MAC address of the next hop. Then the next hop stores the MAC address of the next hop until it gets to the destination. All this tends to occur within seconds. So for example, in a simple connection like telnetting to www.linuxcbt.com port 80, all of that takes place. As quickly as we were able to say so, our local system, the .10 box, stored the MAC address of the router. The router stored the MAC address of our ISP's router, default gateway that is, and up through the chain until we get to our servers, which are based in San Diego. So just like that, the internet has placed us there. And that is a result of the ARP translation taking place. And each and every TCP/IP compliant device performs this sort of ARP or address resolution lookup whenever two hosts attempt to communicate. Now there are many more tools to look at. What we'll do is sprinkle the usage of those tools, such as traceroute, MTR, NSLOOKUP, DIG, and so on, Whois, etc., throughout our studies, rather than spending too much more time focusing in on those key tools. Again, let's just recap some of the important tools that we've covered. No diagnostic tools, of course. From the top, we looked at ping. Ping is the Packet Internet Groper. It sends ICMP, which is a distinct protocol from IP and TCP and UDP. It sends ICMP echo requests and expects echo replies. And it can be customized to send certain packet sizes, certain counts, certain intervals, so on and so forth. Use it to test whether or not a host is available. But it doesn't always work. Beware. Note. Firewalls, one or more, may block ICMP traffic, causing your pings to fail. Telnet is great for diagnosing TCP ports. It helps you to connect to the TCP port and determine very quickly whether or not the port's available from the perspective of the user testing. So if you're out on the internet and you want to determine if a box that should be published from our network is accessible, try to telnet to the port that you know is to be accessible. And if you can connect, then you know you have connectivity. Netstat returns connection information based on information in ProcNet. Again, the kernel maintains information in this dynamic file system beneath Proc, and beneath ProcNet are many 0-byte files that are dynamically updated that Netstat relies on to return information such as current listeners, established sockets, interim connections, or even the routing table, which we haven't shown you. Netstat-RN, for example, returns our current routing table, which tells us that our default subnet is accessible via ETH0 with the following mask, 24 bits. The subnet for automatic IP configuration is available on ETH0 if necessary. And for all other hosts that don't match these two subnets, send the traffic to our default gateway of 192.168.75.1, which is also accessible through ETH0, and it's up and it is a gateway. The U status means the route is up. Let's just add this to our netstat series of commands because it's important, although you could run the route command. So netstat-rn returns the routing table. This is the kernel routing table. In other words, the kernel uses this routing table to determine how to route traffic, depending on the request that's made. So when we issued the telnet to www.linuxcbt.com port 80, immediately the kernel determined, well, www.linuxcbt.com translates to a 71 address, 71.6.192.197, which doesn't match this network or this network, so it has to be sent using this catch-all to our default gateway. Our default gateway, which is the router, then took it upon itself to go and look up on the internet how to get to 71, so on and so forth, 6.192.197. So netstat is useful for determining connectivity information, including the routing table information. ARP, especially when run with the -A option, returns the MAC to IP mappings, and it is useful in determining who those hosts are. ARP is always maintained in a TCP/IP setting, as it is the base or the low-level layer 2 protocol that's used when communicating on various network segments. Again, when you communicate with a remote host who resides on a different subnet, your system will maintain an ARP entry for your default gateway's interface. Your default gateway, which is usually a router, will then determine how to communicate with, in other words, it will relay the communications to its default gateway until it gets to the destination host. Again, this all happens within a matter of seconds or less, since the connections are small and the internet's fast. So those are your key tools, but there are many other tools, many other tools. These are just tools that you'll use frequently.